All right, the last thing we'll do is to take a spectrum of carbon dioxide by filling the cell with carbon dioxide and repeating our measurement. Okay? Of course, we have some data on carbon dioxide already because of the stray CO2 that got into the other files, but let's try and do it carefully. So the cell is all pumped out now. So let's close the vacuum pump. We'll fill it with carbon dioxide. There we are. And then we can go ahead and take our measurement. Okay, 15 minutes later, here's our result. And you can see the CO2 lines clearly as well. Yeah, let's just take a close look at these before we go on. Okay. First of all, we have the main series of CO2 lines. That's what we're going to be analyzing. It looks rather similar to the CO lines, only these are now substantially closer together, which is interesting. We'll come back and look at this again, of course. In addition, let's scan over here and take a look at the low frequency band, the band around 600 wave numbers. And zoom in on that. Let me rescale this. There we go. Now what's interesting here is that once again we see the double set of lines, one on the low frequency side, one on the high frequency side. But in this case we see something else, a strong absorption line in the center. This is called a Q branch, and it corresponds to transitions in which the vibrational quantum number changes, but the rotational quantum number does not. Those are not allowed, those are allowed transitions for this particular vibrational mode, the bending mode, but they're not allowed for the asymmetric stretching mode that we saw before, so we don't see a Q branch there. Let's go back over to here. There we are. And let me rescale. Okay. Now we can reprocess this using the reference data that we already had, because the reference spectrum we took 20 minutes ago is still perfectly valid for this. This is a little hard to see now, but the red trace is the ratioed spectrum, while the blue trace is the original sample data. Let's cut the sample data out of the image now. There we are. So we just have the transmission file. And now let's process this into absorbance so that the peaks go up. There we are. And we'll zoom in a little bit further. And we're ready to go. Now we can use peak pick to find the peak locations in 1 second. We'll go to find peaks. Very good. 1 second, please. Okay, now we're ready to do our peak picking. There we are. Let's adjust the threshold. Oops, too far. And that looks good. We're having to do this a little more carefully because of a complication that I'll talk about in one moment. But now it looks like we have a reasonable set of lines. Okay? I think that's good. Okay, let's stop there. We'll copy the peaks to the clipboard, go to Excel, get a new, oh my gosh, get a new workbook here, and we'll paste it in. Great. Okay, before we leave the carbon dioxide, I want to focus on something interesting here. It's a little hard to see in the in what you're looking at in the video recording, I'm sure. But maybe if we blow it up a little bit, it'll be easier. Maybe not. Let me also zoom in a little bit this way. It's hard to see, but perhaps you can see here that in addition to the very strong lines we were looking at before, there's another series of weak lines here that they're much weaker, but otherwise they look similar, and they seem to be associated with carbon dioxide as well, okay? Something really interesting about this set of lines, which is in the few places where we can see them unobscured by the main spectrum, like here and here, we can see that the spacing between the lines is 1/2 of the spacing between the main lines in carbon dioxide. There are twice as many lines in this spectrum as in the main spectrum, okay? That's really interesting and something we'll want to think about, although it's not the main issue for our experiment. In any event, we have our data now, so we're ready to stop, and we'll turn it over to you. You have a peak table and some graphs that you can analyze. Okay, good luck.